Hello everyone, welcome to AWS Dev Day. I'm Yubo Wang, Principal Developer Advocate at AWS. Today, I'm going to talk about computer vision with transformers on Amazon SageMaker. As we know, computer vision is dealing with how computers can gain high-level understanding from digital images or videos. From the perspective of engineering, it seeks to understand and automate tasks that a human vision system can do. Computer vision tasks include methods for acquiring, processing, analyzing, and understanding digital images, and extraction of high-dimensional data from the real world in order to produce numeric or symbolic information. The scientific discipline of computer vision is concerned with the theory behind artificial intelligence systems that extract information from images. The image data can take many forms, such as video sequences, views from multiple cameras, multiple dimensional data from 3D scanner, etc. The technology discipline of computer vision seeks to apply the theories and models to construct a computer vision system. Subdomains of computer vision include event detection, video tracking, object recognition, pose estimation, 3D scene modeling, etc. In recent years, with the development of cloud computing, developers can enable their applications with computer vision easily from cloud vendors such as AWS. When talking about computer vision, we have to mention about convolutional neural networks, CNNs. The concept of CNNs were introduced in the early 1980s. The thesis behind CNN was to be able to detect objects within the image, independent of its position within the frame, its rotation, or its interaction with other objects. The basic principle of a convolutional neural network is to transform an image into a matrix of value. Using this numeric representation and a series of special neural network layers, we can expose the depth of image and the orientation of pixels and use them to detect patterns. The main components of CNN is a convolutional layer. Its job is to detect important features in the image pixels. Layers that are deeper will learn to detect simple features such as edge and color gradients, while higher layers will combine simple features into more complex features. And finally, dense layers at the top of network will combine very high-level features and produce classification predictions. But convolutional inductive biases lack global understanding of the image itself. They are great at extracting vision features, but they are not able to modelize the dependencies between them. For example, a convolutional layer of a model trained to recognize faces can encode systems about whether the features eyes, nose, mouth are present of the input image. But these representations will not have the kind of eyes above nose or mouth below nose because each convolutional kernel will not be large enough to process multiple of these features at once. Large receptive fields are required in order to track long-range dependencies within the image, which in practice involve using large kernels or long sequences of convolutional layers at the cost of losing efficiency and make the model extremely complex, even impossible to train. So, looking forward to the next generation of scalable computer vision models, we may ask whether the domain-specific design is necessary, or we can find successful leverage more domain-agnostic and computational efficient architecture to achieve state-of-the-art results. As from the original 2017 paper, attention is all you need. Transformers are used in entire input sequences simultaneously. Transformer architectures has achieved state-of-the-art results in many natural language processing tasks. One of the main breakthroughs with transformer models could be the powerful GPT-3 released in the middle of last year, which has been awarded Best Paper at NeurIPS 2020. Novel works have presented technologies that use transformers to overcome the limitation presented by inductive convolutional biases in an efficient way. These works have already shown promising results in multiple computer vision benchmarks in fields such as object detection, image classification, video classification, and image generation. Some of these architectures are able to match or outperform SOTA results even when getting rid of convolutional layers and relying only on transformer. Detection transformer is the first object detection framework that's successfully using transformer as a main building block in the pipeline. It uses self-attention with vision features extracted from the convolutional backbone. This model is able to compute multiple detections for a single image in parallel. The authors of this paper claim that the model outperforms SOTA models in images with large objects. They state that this is due to the higher reception field that self-attention provides to the model. To simplify, in this model, CNN is used to learn 2D representation of an image and extract the feature. The output of CNN is flattened and then supplemented with positional embeddings to feed into standard transformer encoders. The transformer decoders passes the output embedded to a feed-forward network for predicting the classes and bounding box. Vision transformer is proposed recently. It is a vision model based as closely as possible on the transformer architecture without CNN. The core mechanism behind the transformer architecture is self-attention. It gives the capacity to understand the connection between inputs. A major challenge of applying transformers without CNN to image is applying self-attention between pixels. While vision transformer has overcome this problem by segmenting images into small patches, the atom of sentence is a word, and this research defined a patch as the atom of the image instead of a pixel to efficiently tease our pattern. Vision transformer is the most successful application of transformer for computer vision, and this research is considered to have made several contributions, including high accuracy with less computation time for training, model architecture without convolutional network, and efficiency of transformer with small patches. Next, we'll see a demo of vision transformer on Amazon SageMaker. The QR code in the right is a GitHub repository for the source code. Okay, let's get started for the demo and start from the paper first. In iClear 2021, an image is worth 16 by 16 words. Transformers for image recognition at scale introduces the vision transformer. It is a new architecture which leverages mostly standard transformer components from the original NLP-focused Attention is All You Need paper, but applies them to computer vision, specifically to image recognition. In this paper, images are transformed into sequences of image patches representing tokens. It's similar to word tokens in NLP. Then the model is trained in supervised learning on image classification using these patch sequences as input. The researchers have proposed something different in their paper that can possibly be the next big step in computer vision. They show that the reliance on CNNs may not be necessary anymore. Then, let's begin to explore more about vision transformers with Amazon SageMaker Studio. Amazon SageMaker Studio provides a single web-based visual interface where we can perform all machine learning development steps, including build, train, and deploy models. The demo is a sample implementation of Vision Transformer trained from scratch with TensorFlow on Amazon SageMaker. First, we set up our environment by importing SageMaker module and get session and role for future usage. In the demo, the training data we use a CFAR10 dataset. It is one of the most popular machine learning datasets for computer vision. We first download the CFAR10 dataset. And next, we upload the data to Amazon S3. We are going to use SageMaker.session.uploadData function to upload our datasets to S3 location. The return value dataset URI identifies S3 path, and we will use it later when we start our training job. Next, let's dive into Vision Transformer model architecture. And I'd like to highlight several items here. They are only using the encoder parts of transformer, but the difference is how they are feeding the images into the network. As we know, transformer has two parts, encoder and decoder. Imagine we are doing machine translation for now. The encoder takes the input data and produces an intermediate representation of the input. The decoder decodes this intermediate representation step by step and generates the output. For Vision Transformer, understanding the encoder section is enough. Here we can see they are breaking down the image into fixed-size patches. So one of these patches can be of dimension 16 by 16 or 32 by 32 as proposed in the paper. More patches means more simple it is to train these networks as the patch themselves get smaller. And then the patches are flattened and sent for further processing into the network. Here, unlike neural networks, the model has no idea about the position of the samples in the sequence. Each sample is a patch from the input image here. So the image is fed along with a positional embedding vector and into the encoder. One thing to note here is the positional embeddings are also learnable, so you don't actually feed hard-coded vectors with regarding to the position. Here, there is also a special token at the start, just like BERT. And so, each image patch is first flattened into a big vector and gets multiplied with an embedding matrix, which is also learnable, and creates embedded patches. And these embedded patches are combined with a positional embedding vector that gets fed into the transformer. From here, everything is just the same as a standard transformer. The only difference is, instead of a decoder, the output from the encoder is passed directly into a feed-forward neural network to obtain the classification output. And let's look at the code and examine each step. This is our model architecture code. We can see in our vision transformers, we have many parameters, including image size, patch size, layers, classes, height, dimensions, etc. In our code, first, image is split into fixed size patches. In our parameters, image is of size 32 by 32, and the patch size is 4 by 4. Then there will be totally 64 patches for each image. Next, we flatten the 2D patches to 1D patch embedding and linearly embed them. Each patch is flattened into a 1D patch embedding by concatenating all pixel channels in the patch and then linearly projecting it to the desired input dimensions. And then position embeddings are added to the patch embeddings to retain positional information. The transformer is agnostic to the structure of the input elements. We add these learnable position embeddings to each patch that will allow the models to learn about structures of the image. We also add a learnable classification token to the patch embedding at the start of the sequence. This sequence of patch embedding vectors will be used as an input sequence length for the transformer encoder. And then we feed sequence as input into a standard transformer encoder. Our transformer encoder consists of a multi-head self-attention layer. It's to concatenate the multiple attention outputs linearly to expected dimensions. The multiple attention heads help learn local and global dependencies in the image. Also, a multi-layer perceptrons. It contains layers with glue activations. And layer normalization. It is to help improve the training time and generalization performance. And last, residual connection allows gradients to flow through the network directly without passing through nonlinear activations. In classification, the fully connected MLP heads as output provides the desired class prediction. The main model can be pre-trained on a large dataset of images, and then the final MLP heads can be fine-tuned to a specific task via standard transfer learning approach. Next, we look at our training script. The training script provides all the code we need for training and hosting a SageMaker model. The training script is very similar to a training script run outside SageMaker, but we can access useful properties about the training environment through various environment variables, including model directory, number of GPUs, channels, hyperparameters, etc. A typical training script loads data from input channel, configures trainings with hyperparameters, trains a model, and save a model to model directory so that it can be hosted later. Hyperparameters are passed to the script as an argument, can be retrieved with the argparse instance. In our training script, we use NMW optimizer. The NMW optimizer decouples the weight decay from the optimizing step. This means that the weight decay and learning rate can be optimized separately. Then we use Amazon SageMaker to train and deploy a model using our custom TensorFlow code. The Amazon SageMaker Python SDK makes it easier to run a TensorFlow script in Amazon SageMaker using TensorFlow Estimator. To start, we use the TensorFlow Estimator class to train our model. When creating our estimator, we make sure to specify a few things, including entry point, source directory, framework version, etc. After creating the estimator, we call fit, which will launch a training job. We use Amazon S3 URIs, where we uploaded the training data earlier. I have run the training before, and it took a while to complete. In the backend, SageMaker sets up a training environment by preparing the instances for training, downloading input data, downloading the training image, then do the training job. We train with 50 epochs and can see the training loss, accuracy, and validation loss, accuracy. When training is finished, the model is uploaded to S3. If any issue found during the training process, we can easily use Amazon SageMaker experiments and SageMaker debugger to find and resolve problems. After we train our model, we can deploy it to a SageMaker endpoint, which will serve prediction in real time. To do so, we can simply call deploy in our estimator and passing in the desired instance type and the number of instances for the endpoint. Then we can invoke our endpoint. Here, let's use the test dataset for predictions. With the data loaded, you can use it for prediction. And with the prediction, we can calculate our model accuracy and create a confusion matrix. Our average accuracy is around 60%. And aided by the colors of heat map, we can use this confusion matrix to understand how well our model performs for each label. Finally, to avoid incurring extra charge to AWS account, let's delete the endpoint we created. Here are some thoughts from our demo. We can see that after 50 epochs, the vision transformer model achieved around 60% accuracy. But this is not competitive results on the CFAR10 dataset, as a ResNet 50 trained from scratch on the same data can achieve around 67% of accuracy. But this is a similar results as reported in the paper. The reason why vision transformer achieve lower performance to convolutional neural networks when trained from scratch on a mid-sized database because of two reasons. The first is the simple tokenization of input images fails to model the important local structures, such as edge and lines among neighbor pixels, so leads to low training sample efficiency. The second is the redundant attention backbone design of vision transformer leads to limited feature richness or limited training samples. So let's go back to the paper and see how the researchers have done. The authors of the paper have trained the vision transformer on a private JFT 300 million dataset, which contains 300 million images, which results in state-of-the-art accuracy on a number of benchmarks. Also, there are pre-trained models. The pre-trained models include base, large, and huge. The base and large models are directly adopted from BERT, and there are also larger, huge models. For instance, VITL16 means a larger variant with 16 by 16 input patch size. The transformer's sequence length is inversely proportional to the square of the patch size, so models with smaller patch size are computationally more expensive. You can see the results as model VITH14 and VITL16. These are two state-of-the-art of CNNs. Another interesting point in the paper is attention map visualization to understand the vision transformer process. It provides more explainability for vision transformers. And let's switch again to SageMaker Studio. As we know that the state-of-the-art results reported in the paper are achieved by pre-trained vision transformer model using the JFT 300 million dataset, then fine-tune it on the target dataset. So, if we'd like to improve the model quality without pre-train, we can try to train the model for more epochs using a large number of transformer layers, resize the input images, change the patch size, or increase projection dimensions. Besides, as mentioned in the paper, the quality of the model is affected not only by architecture choice, but also by parameters such as learning rate, optimizer, void decay. So in practice, it's recommended to fine-tune a vision transformer model that's pre-trained using a large, high-resolution dataset. So, using Amazon SageMaker automatic model tuning is an efficient way to fine-tune the hyperparameters of pre-trained vision transformer on the target dataset. More recently, Hugging Face released Vision Transformer model, and we know that AWS and Hugging Face together has announced Hugging Face deep learning containers to make it easier to train Hugging Face transformer models in Amazon SageMaker. This is Hugging Face Vision Transformer model. And this is how to train Hugging Face models in Amazon SageMaker. We can see it is very similar to using TensorFlow estimator for training. And that's all for the demo. If you are interested and have more time, you can deep dive into the paper and do more experiments on Amazon SageMaker. Let's move back to slides, and this is the summary of my talk today. While convolutional neural networks have revolutionized computer vision, we believe that vision transformer is a preliminary step towards generic, scalable architectures that can solve many vision tasks, or even tasks for many other domains. We are quite excited for the future development of vision transformer. And also, Amazon SageMaker can speed up overall machine learning processes for fast iteration and experiments. For more information, you can visit aws.amazon.com/SageMaker. That's all for my presentation today. Thank you and goodbye.